Available, so we'll archive it in our website. So you all know the URL. So you can go there after 2 days and you can find the slides there. So.
Okay, thank you. So if you wait for 2 days, you can find it there. If you wait till I get online, you'll also find the slides on my webpage. Actually, I put all my slides online, so if you find something else interested, there is more slides from tutorials I've given before. I stopped at this point because there is one more curve shape or one more way of representing curves I want to present here. And in the break, I got the question about how many secure curve shapes there are. To make that clear, is we have an elliptic curve is some geometric object. I can give you a very abstract definition of this thing. You have this thing up in the air, and then writing down a curve equation is kind of projecting it into some plane. If you want to have it in xy with x squared and y squared, you project this way, and then you get that the curve equation is x squared plus y squared equals 1 plus some coefficient x squared y squared. The same elliptic curve you can project in a different way, and you get a Weierstrass curve. There are many more curve shapes. Sometimes these curve shapes require that the curve has a point of order 4 or a point of order 3, but for curves which have these points, there are different ways of writing them out. They are all equally secure. The security of the elliptic curve does not depend on the way I write it. It depends on the number of points being close to a prime number. It can be 2 times a prime number, 3 times or 4 times a prime number, but it shouldn't be a product of lots of little prime numbers. You would like that the group order is prime, essentially. When you're working with Edwards curves, there's one extra development due to Montgomery in '87. He was actually not looking for elliptic curve cryptography as much as he was trying to factor integers. So there's a funny thing when you make elliptic curves faster, if you make the arithmetic on elliptic curves faster, you're actually making factorization easier. So Montgomery was using the elliptic curve method of factorization for breaking RSA, or generally for factoring integers, and he came up with a different way of writing elliptic curve addition in something which is, well, essentially a Weierstrass curve. It's a Weierstrass curve, but there is an extra parameter b, and it's specialized so that there is no constant term and that the linear term here is 1. And what you observed is that you can write the x-coordinate of 2 times a point purely in terms of the x-coordinate itself. So you take the x-coordinate of 2xy, and you get it in terms of the x-coordinate of the point. Okay, fine. As a mathematician, I can explain this. That comes from division polynomials. I go like, yeah, proceed, proceed. He then also goes like, I can also write the sum of 2 points. You give me 2 points, x3, y3, and x2, y2. If you give me the x-coordinate of the difference of the two, then I can write the x-coordinate of the sum of the two, it's x5 here, in terms of the x-coordinates of the 2 input points and the difference point. So if you think of what we did before, for the Edwards curves, we had x and y, and then we wrote them as x divided by z, y divided by z, using 3 storage locations. Montgomery's idea was, well, keep on doing that. We don't want to do the inversion, so we do this in a projective way as well, x divided by z, but we only need 1 affine value or 2 if you go for fractions. So he saves a little bit of space. And also, compared to what we knew back then as how fast elliptic curve addition was, then if you write out the doubling formulas and the addition formulas in these coordinates, so taking x divided by z here and there, then the number of additions is smaller than what we need otherwise. So the doubling costs you 2 multiplications and 2 squarings. So looking here, there's the 2 squarings, here and there is the 2 multiplications. These are the 2 multiplications, and here's a multiplication by a constant. We call this constant multiplication. So the doubling is faster than what on the Weierstrass curve would happen. The addition, this thing here, is also pretty fast, just 4m plus 2s. I was advertising before that Edwards curves take 10m and said this is a good thing. This looks like it's far less, except for there's this condition that I need to know the difference of the 2 points. I need to know this x1 and z1 in order to compute the sum of the 2 points. So it's not a normal addition, it's something which we call differential addition. It's an addition of 2 points where I know the difference of the 2 points. So it's different from the addition that I showed you before. Now, you can use this doubling and differential addition to do a scalar multiplication. For instance, if I start with p, then I can compute 2p. If I have p and 2p, then the difference of the two is 1p. So I have all the information I need to compute 3p. Now I have p, 2p, and 3p. The difference of those two is p, so I can compute 5p. If I have 3p, I can also compute 6p, because the difference between 3p and 3p is 0p, which I also know. So just by doubling this point, I get there. Now I have those 2 points, then I can say add those two because I know the difference. So I can kind of bootstrap. I'll give you a formal description of this thing which we call Montgomery later on a later slide. So I can use it to do scalar multiplication. I can't do a general addition, but I can use this differential addition to compute multiples of a point. So the number of additions, the number of doublings is again the logarithm of the scalar, but for each bit I need to do an addition and a differential addition. So I can't just do, oh yeah, this is a cheap addition. I always need to do both operations, a doubling and an addition. So these speeds are pretty close to what I get for an Edwards curve, as I explained it so far, but I can do more tricks on Edwards curves. So nowadays, for instance, if I use it for factoring, then Edwards curves beat the implementations using Montgomery curves, but Montgomery curves are still a very nice representation. It's kind of surprising that it's enough to look at the x-coordinate. You don't need to worry about the y-coordinate. So if you somehow only need 1 point, say you're doing a Diffie-Hellman key exchange, then you can use the Montgomery coordinate system with this operation to do the computation. However, thinking back to the elliptic curve digital signatures, there we needed to compute this expression. So we had the W1 times P and W2 times PA. In general, if you have 2 scalars and 2 points, then you end up having an addition in there. An addition you can't compute, you can only compute differential addition. You can bootstrap from that, but it's not really very efficient for that. So it's good for Diffie-Hellman, it's not so good for ECDSA. If you would like to see more curve shapes, if you want to have the best addition formulas for a curve which has a point of order 3 and not a point of order 4, then for instance Edwards is not the best thing. There's something called Hessian curves. They always have a point of order 3 on the curve. We have a database where we try to keep it up to date. I'm sure that we don't have the latest formulas. So if you're the author of a paper which has faster formulas or different formulas, and we have shamelessly forgotten to include your formulas, please send us an email. Preferably send us an email including text that we can just use. So we have a database of curve shapes and addition laws there, and all the addition laws that we publish, like addition law means something which then gives rise to operation counts, like here, everything is computer verified. But if you send us the inputs to the computer verification, we'll run the script, we verify that your operations is correct, unless it isn't, and we'll put it online. So we kind of asked for help in keeping up to date. We know right now we're missing a few, maybe Christmas holidays or something like this, we might find the time to update it. But it's pretty up to date. It's certainly, if you take, say, the NIST standard for how you're supposed to implement elliptic curve cryptography, for the same curves, you'll find faster formulas on this page. So it stands for elliptic formulas, explicit formulas database. So we have a database of elliptic curves over prime fields and over binary fields, and well, basically whatever you send in will get there. So at the moment we have 13 different shapes. Then for each shape you can have for instance, projective coordinates or funny shaped projective coordinates where you divide 1 by z squared and 1 by z cubed or something like this that gives an extra thing here for the number of representations. And then sometimes people publish faster and faster and faster formulas. So for each of those shapes, we have at least one, if not more, computer verified formulas. So a total of almost 600. Good. I promised that I would tell you how to do arithmetic faster. What I showed you so far was saying to compute k times a point or n times a point, we write n in binary. So here the ni are 0 or 1. And then we use this binary representation starting from the most significant bit in the computation. So instead of computing p plus p plus p, we do the following. We start with the most significant bit. We take the p, we double it. So we put it on r, then we double it. If the coefficient is 1, then we add it. So this is what I had on the slide before for the example 23. Here's now an example with 35. So every moment when you do here the computation, at this point you have doubled, then you added the next coefficient. If it's non-zero, then you double and so on. So at every moment you have the top part, the leftmost, the most significant bit, till the ith bit. So that's why it's called left to right. You can also start scanning your scalar from the least significant bit. You start with the smallest one and you go up. So what we do here in the right to left binary is we have a point q which will contain a power 2 to the power I plus 1 of p. So you start scanning, is 1 in there, is 2 in there, is 4 in there, is 8 in there, and each time you add this multiple in there. So if you would see just these powers of, well, the powers of 2 times p pre-computed, you would just select the bits according to n and do a few additions. Now, that would require a lot of storage, and if you don't see, say if this point came in as a Diffie-Hellman key exchange, you're not going to see this point again. You don't want to do that many pre-computations. So for every bit, in both cases, you do one doubling. Here you do the doubling onto the intermediate point. Here you do the doubling on a point which contains 2 to the power something times p. So here is scanning from the right, here is scanning from the left. Both of them have their advantages. Here I need only one variable that I touch. The p is always the same. I might add it, I might not add it. Here I'm writing to q and to r. If I want to reduce the number of additions, so I keep the number of doublings the same, or about the same, because that's the bit length. But if I want to reduce the number of additions, then where I'm starting from is I have two values, 0 or 1. So with probability 1/2, it's a 0. So if I have L doublings, I'm expecting about L over 2 additions. Now, if I am in a case like an elliptic curve, where taking the negative of a point is a cheap operation, then I might want to go for something called a signed representation. Not only 0 and plus 1, but taking 0, plus 1, and minus 1. So here's an example of a number which is very close to a power of 2, just one less. So if I want to compute it in left or right binary, then I have everywhere a 1. So I need to do one addition for every bit. Now, 31 is just 32 minus 1, and 32 is very easy to compute. It's lots of doublings, then I'm at 32, and then I just remove 1p. So the number of doublings has increased because I'm doing one extra bit, but the number of doublings, number of additions went down significantly. So systematizing this is whenever I see two adjacent ones, I replace them by a minus 1 in this lower bit and put in zeros in the middle and then scoot over with 1. So I replace any number of adjacent ones by putting a minus 1 here and moving the plus 1 over by 1. So it might get longer by 1 bit, but the number of ones won't increase, and generally it would decrease. So if you have such a thing where you never find two ones next to each other, That's called a non-adjacent form. So these things are adjacent, and you want to have at least one space between those. To compute this nav, I'll show you the algorithm. The nice feature is if you look at all representations which use coefficient 0, plus or minus 1, then those have the lowest number of non-zero coefficients, so the lowest number of additions. So let's see what happens here. Here is my binary representation. I start scanning from the least significant bit. I find two adjacent ones. Then I use the rule over here. I put in a -1 in this position, put a 0 there, and then have the 1 come over to here. Now I found another two adjacent ones, so I change this again to a -1, then the 1 goes over and find these guys, and then I replace the -1 here, this goes over here. Okay, so this is an example for, it doesn't make things worse, but it doesn't really seem to help much. Because whenever there was this run of ones, there was another 0 before it came. If I would have a long stretch of ones, then you really notice that the number of additions goes down. So here's an example where you notice that, the 31 was an example where you really notice that the number of additions went down. Here, well, it stays the same. So if you get such an integer, you don't want to tell your computer, well, now go scan for those things. So here is an algorithm, which I just put here because the slides will be online, so I'm not going to go through the details. But it does the same that you, as a human, would do by taking the next string of ones, putting a -1 there, pushing all the zeros in here, going 1 over. There are ways also to start with the most significant bit. So if you're thinking you want to do a left to right algorithm and want to compute this on the fly, that can be done as well. So here's an example how we get the nav for 35. So we get this input, we run through the steps, and after 2 slides, we come out with what I had on the previous slide. So this is, in fact, working. The little s on the bottom, I used to have a 2 there. Now it's an s for signed representation. So the bar over means it's a -1 instead of +1. Now, it's nice to have plus and -1, and so if you're on a smart card, then you might be very concerned about your storage. You get the -1 for free. If you have x, y as your point, then when it's Edwards curve, then the minus point is -xy. If it's a Weierstrass curve, you have u and v, then the negative is u comma -v. So it's very easy to negate a point. Instead of adding a point, you add the negative of the point. So you don't have any extra storage. You just, instead of adding p, you add the negative of p. But what if your storage is not so restricted and you would really like to push down the number of additions? Then you go for something which we call windowing. So instead of searching for strings of ones and replacing them, let's do the following rule. We write this as we allow coefficients in this, and we group them. So we take, say, 2 bits together. Instead of writing something base 2, we write something base 4. So for instance, here we have something written in base 2. Now I write this as 1, 0 is a representation of 2. So it's still binary. I'm still having the same number of digits here. I'm replacing 1, 1 by 3, 0, 1 by 0, 1, 1, 1 by 3, so on, so on. Here this is a 2. And then I say, oh, now I make it a representation base 4, so I kick out all the intermediate zeros. So this is just grouping them together. Now, if I pre-compute p, 2p, and 3p, keep them, I'm reducing the number of additions. The number of doublings is still the same because I need to do 2 doublings in between everyone here, but I kind of almost halved the number of additions. There are more options, so this one is going to the full interval to the power of something. I can also use fractional windows, so I'm not going to all the way of the power of 2. So if you're more restricted or if it really hurts you to do all the pre-computations, then you can play with what coefficients you're taking here. So the general one is you group W bits and you go from 0 to the W. Now this doesn't quite have the same feature as enough yet. You would have like adjacent coefficients and they still stay there. You don't actually notice that you would do much better instead of grouping, say, was an example. Would like to group them in a slightly different way, like you might want to group those together and have it spill over there. So what you rather would do is slide a window, not be fixed, cutting it into two pieces, but sliding in some way that you get more coefficients together. And, oh yeah, here, sorry. This is what I want to point out. So here's two ones, which at this moment cost us two additions, but if I would group them together like this, then I would have just the doubling, one addition with 3p, which I have pre-computed, and then another doubling. So it might be better to slide the windows instead of having a fixed window. So if I slide like this, if I am willing to go from here, slide till I hit a 1, then I replace these two by a 3, then I have a 0 there, then I take the next one, and I realize, this is a 5, and 5 is the same as minus 3 mod 8. So if I go for positive and negative coefficients, I can replace the next ones by a minus 3 here. Then I can slide on and on and on. So this reduces the number of additions quite a bit more, while not having the number of pre-computations explode. So for elliptic curves, if you're computing 2p, if you're computing 3p, you automatically also have minus 3p. And it feels kind of wasteful to pre-compute 2p, because you're going to do the doubling anyway. So instead of computing 2p here, you first just have a doubling and then group those two together. So sliding window methods bring down the number of additions even more. I said before, you have to pay for these pre-computations. So when you get your scalar, when you get your point in the Diffie-Hellman key exchange, you start doing the pre-computation. So at that point, you sit down and compute p, 2p, 3p, 5p, 6p, and whatever you need. But sometimes, for instance, the first step of the Diffie-Hellman key exchange, Alice knows p. It's always the same p. It's a fixed base point. Or if she's computing signature, it's a fresh nonce. Don't forget the PlayStation does. It's a fresh nonce each time, but it's the same base point. Now this point she stores on her PC, and if it's a PC and not a very storage-restricted smart card, she can do this computation much faster. So thinking of the right-to-left method, there were all the powers of 2 times p. If she has them pre-computed, she can just plug them. If the bit is 1, she adds it. If the bit is 1, she adds it. So no more doublings. So if you go through the effort of storing all these powers of 2 times p, then the scalar multiplication, you just add. There's no more doublings. All the doublings have been done in the pre-computation phase. It's expensive in the pre-computation phase. You don't want to do this for every point from scratch. But if it's the same point all the time, you just store those L points and you're done. If you're even more interested in speed, if you're not restricted by storage or whatever, you can do a combination of what I showed you so far with the windowing method. So instead of just computing the powers of 2, you compute the powers of 2 with some scalars. So you group them, like the little 2 by 2 thing here. So here I'm having the same example with a base 4. If I now pre-compute not only 2p, 4p, 16p, and so on, but also for all the 1, 2, and 3 as possible scalars here, then I have half the number of additions that I need there. I'm having less chance of hitting a 0. Before that, I had a 50% chance of hitting a 0. If you get larger and larger windows, then, well, almost all of them are additions. But instead of 16 additions, it's just 8. But it's a large pre-computation. Then the final one in this how to do scalar multiplication is the Montgomery ladder. So think back to the Montgomery curve that we had at the beginning of the second part, where I said you can double, or you can add 2 points when you know the difference. And the example I was showing you is you're walking with 2 points which always have fixed difference 1. We are going from 1p, 2p, 3p, then 5p, and 6p, and 11p. So here's the formal way of doing this. You write your scalar, you write your n with the same binary representation, and at every moment you have 2 points. You have Ri and Qi. And the difference between the Ri and the Qi is just 1p. R is Q plus p. So these 2 points will be always at fixed difference p. So the reason it's called ladder is, well, if you look at a ladder, then you have 2 strands on the side, and then you have the bars across. All the bars have the same distance. So this is like always distance p. You climb up your ladder, but you always stay at fixed positions. R and Q will always be difference 1 apart. So we never have to update the difference 1. So in all the differential additions, we know the difference is just the base point. Now to do this is, if the bit is 0, then we double the Q point, that's the one which is smaller by 1p, and here we add those 2. Well, we can add them because they have difference p. Now this is 2 times Q, and this is Q plus p. So both of them are 2Q, and then this one has an extra p value. So here we doubled the smaller of the 2 and then added them. Now if the bit was 1, then we add the 2 in the first component and double the larger of them. So this is 2Q plus p, and this is 2Q plus 2p. So again, the difference is p, but compared to the bit non-set, it's a difference of p in both coordinates. So as an example, if I write 13 in binary, it's 1, 0, 1, 1. I start with the most significant bit. I write, well, p and 2p, I compute this value. Then the next bit is a 1. So I'm in the bottom part here. So I add the 2 points into the first coordinate, and then I double the second point. Okay, then the next step is I find a 0, that is this top line. So I double the first coordinate and then add them into the second part. And then the last bit is a 1, so I get 6 plus 7, which is indeed a 13. Put it in the first one, and well, I'm supposed to finish my computation, so I put a 14 here. First of all, well, this is a fairly easy algorithm. It's just similar to binary double and add, but for each step I do 1 addition, 1 doubling. So far I've just talked about efficiency, but I also, when I do implementations, I'm concerned about security of the implementations. I must assume that somebody is seeing what I'm doing. For instance, you listen to me between the time that I get the Diffie-Hellman key exchange, I get the point in, and then I output some ciphertext. That time in between is like 1 AES computation, which has pretty much fixed time, and 1 computation of a scalar multiple. And I'm always going to use my secret key. Now, if I have my secret key of a very low density, very few additions, then you'll notice that in the time it takes. So you might be listening on the time that I'm taking for computations, or you might be sitting on my computer and checking, do I do an if or else computation? If I do it like this, then I also have an if and else. You would see whether I'm doing 0, then I do something immediately. If I do the else, then I wait a moment in my computation and then jump on the second one. So even on a PC, you do see differences if you have conditional branching. It's even more the case if you're doing smart card implementations. Then you have to deal with attackers who not only listen to the timing, but they can also get, say, detailed power consumption information on every point where you're consuming it, and they can get the electromagnetic radiation. So if you're dealing with a side channel attack on a smart card, it's much more severe than on a PC. But even on a PC, you have to deal with people who get timing information or who might be running a different process on this. Like you have a hyper-threading and you have a different user there and he might be spying on what you're doing. Or this person might be, well, filling your cache line and seeing what comes out of it. Now, this operation is already more uniform than in the left to right binary that I showed you before. In the left to right binary, if the bit is not set, you see a doubling. If the bit is set, you do a doubling and an addition. But that's kind of wasteful. Additions are more expensive than doublings. So if you're in that situation, then looking at this information flow, you naturally always do one doubling, either here in the second part or the first part, and you do one addition. I wrote it as an if-else condition, but I can do this if-else as an arithmetic instruction. So I can mask the points, and I can always first compute the doubling and then compute the addition. Even, well, I just need to write to the correct coordinate. So I always would do the doubling first and then map it to the right thing and then do the addition. So if you're worried about side channel attacks, then Montgomery gives you some benefit. Another thing, you can also, if you stay on Edwards curves, you also have side channel benefits that you don't get on the Weierstrass curves, because every doubling can be written as addition. So you can write your whole scalar multiplication as addition, 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 still using that you double a point or add a point, but the side channel attacker only sees an addition each time, because you can use the addition formulas for doubling. It's a little bit wasteful because the doubling formulas are faster, but you could do it. What we recommend for Edwards curves is you reveal that you're doing doublings and additions, but you make this information uniform, you make it predictable. So here, this is like the mother of all predictable algorithms. It's always one addition, one doubling. It's just that the data changes. Now for CPU implementations, the attacker does not have so detailed information that he knows which register I'm reading from. If I'm on a smart card, I have to be a bit more careful. I have to really figure out what he can see. If he can see the whole information flow, then I'm pretty much lost. So then I need to appeal to my hardware friends and say, well, give me some more security so that people don't see exactly where I'm coming from. And then, well, math can help again. But if you're on a CPU, then this is pretty neat. If you're in the situation that you're computing the verification step on the signature scheme, so you're doing ECDSA, then I said you have two scalars. And I said Montgomery is pretty bad there. But let's forget about side channel resistance for a moment. Let's just try to get the fastest implementation possible. Let's assume we have, well, not just two, but maybe many of scalars. And we write all of them in base 2. And then we align them here. This is all power 2 to the 0. This is all power 2 to the 1. This is all power 2 to the L minus 2. This is all to the L minus 1. Then if I want to compute not every individual scalar multiplication, but I'm just interested in the sum of those, then I can group all those doublings together. I still need to do all the additions, but I can group the doublings. So if I compute this point, then I start with taking the first column. So I take this many times P1, this many times P2, this many times PM. Take those. And then just in the left to right algorithms, I double this. But there's just one doubling for all M points together. Then I scoot over to the next bit, this one, the red ones. And then I add this many times P1, this many times P2, up till this many times PM. Here we go. And then take the whole thing and double it. And then add, well, the next one, so go always column-wise. So what happens now is I have as many additions as I had for the computations of the M individual computations, but I only have 1 times the doublings instead of M times the doublings. So if you have a scalar multiplication with lots of scalars, you can reduce the doublings to just a single set. So in the ECDSA set, we have 2 scalars. So I can do this on the 2 points, or I can be more adventurous and say, well, there's always the same P. So I do a pre-computation of half the length. So then I split my scalar. So I artificially create 2 scalars. Half of the bits times P, and the other half of the bits, the higher bits, times this point. There's another system which is called GLV, which is curves with endomorphisms, where instead of having this way of computing R, there's actually a cheap way of computing some similar R. You naturally get 2 scalars. So we do often see 2 scalars just in normal systems, and even if it's just a single scalar system. So in all of those cases, you would like to use the joint doublings.
Tanja,
Yeah. sorry.
So in this sort of pre-computing of your doublings sort of situation, if you're worried about the scale, the side channel tax, can you just do your pre-computing of the doublings and then assume that you're going to have, and then be wasteful in the sense that you assume like half ones and you do that many additions, or is that like, or you do lose all the benefit for that?
Okay. So the question was, what happens if I'm still, so going back to the size scenario and going to the pre-computation scenario. So I have all the powers of 2 times p pre-computed. Yeah? Then on average, I'll have half of the coefficients being set. If I want to handle all integers, I have to assume the worst case that all of them have 1s. So for each one, I have to add it. Now, what we call double and always add, in this case, would be an addition for each point. So I do either an addition that I want to have if the bit is set, or I do something like a dummy addition. So I do the same computation, I consume the same power, I consume the same time, but instead of writing to this variable, I write to some other variable that I'm not going to use. So yeah, this is a method how I could avoid it. This is actually a method that we are using for the sort library. We're doing it with the pre-computations. So I wouldn't want to do it if I just have bits 0 and 1. But if I have bits 0 till 15, then it's just 1/16 of a chance that the bit was 0. So it's not so wasteful then. So if I have large enough windows, then the dummy additions don't cost me so much. And that's when we do this. So then we get size uniformity by doing dummy operations. But that's in the scenario where we have a fixed base point. If you have a variable base point and you don't need to have general additions, you might be just as well happy with Montgomery. Because then you do an addition and a differential addition, which is cheaper than an addition, than a doubling and a full addition. So differential addition is cheaper than full addition, which you would have to do with the dummy operations. So it depends on the scenario. If you're a fixed base point, then do that. If you're a variable base point, then you're happy with Montgomery, unless you need to add afterwards. Did that answer the question?
Yeah.
Good. So now with the joint thing, so here are some cases where we come in. If you want to accelerate the verification even further, instead of splitting your scalars into 2 parts, you can split them into more parts. For instance, you know 1 is a scalar multiple of the base point, where you can similar do some pre-computations. That would then give you do like 3 parts of this one and then have the other one come in. There's also a proposal which uses 6 coefficients. So out of one ECDSA computation, you can break it down into a 6-fold scalar multiplication, so you reduce the number of doublings accordingly. More interestingly, if you are a server where you want to verify all signatures coming in, say if you're sitting somewhere, you have lots of traffic, but you're only willing to route the traffic any further if there's a signature on the message. Then you have enough signatures coming in that you can wait till you have 60 signatures and then verify all those 60 signatures as one batch altogether. You assume that most of those signatures are okay. If that's your, if you're under attack, then you'll always find invalid signatures. But if you're assuming that things are fine, you just want to double check, you want to make sure that nobody's attacking you, then you do a batch of 60. If all of the 60 are good, you can just verify them with one big computation. And that's also where we can use these joint scalar multiplications. If you then find that one of the signatures is not valid, then of course you have to go back and checking all the 60 one by one. But if you want to check a whole batch, you do a random linear combination, do one scalar multiplication with many scalars, and you're good. So here's an example of the ECDSA type. So you have 2 points, P and Q. You have 2 scalars. And if you do them one by one, then, well, you have 10 doublings here, 10 doublings there, and then, well, 6 additions here, 6 additions there. If you do the joint doublings, if you do the column-wise, then of course the doublings goes down to 10, just 1 per bit. And you notice here that we have a p plus a q in this column. Also in this column, we add p plus q. Also here. So if both bits are 1, we are actually adding each time p plus q. Now by pre-computing p plus q, we can, well, reduce the number of additions to at most 10 instead of at most 20. So that's another cute trick, that you pre-compute like these combinations, or you go for negative coefficients and you compute p plus or minus q individually. So next, what's on the next slide? Okay, so here, I don't know, I removed one slide or I didn't retake. I thought there was one more. So you can also do something if you have negative coefficients and you want to reduce the number of doublings and addition jointly. Okay, so how far can we go? Is there any limit? I mean, of course, if I do pre-computation, then I can reduce the number of computations to just a table lookup. But it would be a really huge table. If I'm not allowing table lookups, if I have to do every computation from scratch, then we have theoretical results due to Brouwer of how long it takes to do a scalar multiplication. So if you want to compute something n times p, where n is less than some bound, then it's about the logarithm. So it's about the number of bits, but you can reduce it by doing some pre-computations on the fly. So the best ones are like 1 plus 1 over log, this number. We do have an algorithm which computes a multiscalar multiplication due to Strauss, which gets very close to this if you have k inputs. So this is actually an algorithm. This is a bound. This is so both of those are faster than the left to right. So you don't have this regular pattern or anything, but you can get to something small like this. And the theoretical bound is also fairly close to this. And here it's just k times more. This looks pretty good. Then Zhao came along, got another algorithm improvement for k-scalars, and then Pippinger. Okay, so lots of stuff. This part was Dan pointing out, and I kept it on the slide, that if you're reading the Bible, if you're reading Knuth, then Knuth is almost always right, except for when he summarizes the competition of how fast can it be to do k times a point. Then Knuth says that Pippinger is not faster except for, well, it is faster than Strauss and Zhao if you have many, many points. Okay, now when we do batch verification, we go for pretty large batches, which means the differences between the numbers are not actually that big. And there's a nice idea due to Boss and Costa, so you might wonder, is this already all? And so the Boss-Costa idea is you write your scalars in decreasing order, and then you go for the differences between the two. So if n is larger than n2, then you look at the difference. Well, actually, you do n1 modulo n2, and you find the quotient here, and then you add this one here. So we split the computation of n1p into something which goes into the n2, and we remove the part of the n2 from the n1. So we've now made this coefficient much smaller, this coefficient stayed the same, but we have a new point. So we've changed k points into k plus 1 points, where one of the things has gotten smaller. Well, we replaced the p2 point by this one. Okay, so at every step, we take the two largest coefficients. We change the definition of the point with a smaller coefficient, so instead of p2, we override it with q times p1, and we make the top coefficient smaller. Then this one goes down, then this one comes in, and then in the next step we have n2, n3, and then the next one goes down, and so on. So it's a fairly simple algorithm, which I have here an example of. So let's assume that these are our scalars. We have to compute this many times p's. Then here are all these numbers, and well, 300 is the largest. 146 is the next largest. So we'll take 300 minus 146, and it just fits in there twice. So we take it away once, so we end up with 154. Then we remove it one more time, so we have 8 left. Now, this one has got much smaller, so it goes at the bottom of the stack. Then we have 146, we have 77 left. We have done the addition of the point P1 plus P2, overriding the definition of the P2. That's the 2 additions that come in here. And now we do the same game here. The 77 fits into the 146 just one time. So we remove it there, go to 69, and have to add the points corresponding to it. Then we have the top ones being 69, 77, so we remove the 69 from the 77, go down to 8. And now you already see that we end up having the same coefficient show up. So now if those two ever get merged, then it's just one scalar multiplication, 8 times something. Okay, so we go down with the 32 and 69, remove it twice here, then we remove the 16 from the 32, and now we have brought one of them to 0. So at this point, the number of points that we're considering reduces. So then we have 16 and 8 goes to 0, then the 2 8s go to 0. Well, they get merged, then we have the 8 goes to 5, then we have this goes to 2, then we have the 3 goes to 1, then we have the 2 goes to 0, and this 2 goes to 1. And now it's just all ones here. So it goes to 0, 0, 0. So in the end, what we're computing is 1 times some point, 2 times another point, 3 times, 5 times, 8 times. So each time we multiplying by some scalar. We never grow to more than k points. We don't need extra storage, so it's a nice, straightforward algorithm. Some brief advertisement of the SALT library before I hand over to Dan. So NaCl stands for Networking and Cryptography Library. Well, for this one, the crypto part is interesting. Also, our implementations have focused on getting the crypto part to work really nicely. Networking is still a bit of a prototype thing. We recently put a paper on ePrint on explaining more of the features of the library. We have also a web page where you can read all the advertisement text. But to explain to you what is in there from a cryptographic or mathematical aspect. So we have 2 main components. We assume that our user, well, what you want to do on the internet, you want to communicate with somebody. Now, this communication should be authenticated. You always want to make sure you're really talking to the person you think you're talking to. And usually you also want to make sure that this communication is encrypted. So one of the 2 primitives that we focus on is an authenticated encryption. So that one starts with doing a Diffie-Hellman key exchange. And, well, we fix one curve. It's a curve over a prime field, which we write in Montgomery curve, Montgomery form. So the prime is 2 to the 55 minus 19. And then we show a curve which is good for arithmetic, meaning that the parameters are small, so the multiplication with the Montgomery parameter A don't cost us much. When we do this Diffie-Hellman key exchange, we can use the Montgomery ladder, so we have an easy time doing a security against side channel attacks on this one. Then we have the outcoming point, we have a point on the curve, and we use that in symmetric crypto. So if you want to have your message, then you first do the public key crypto part here, you do a Diffie-Hellman key exchange. That's totally independent from the message that you want to send. Okay, now you and the server, or you and your communication partner, have one shared key. Then you use this key that shows another thing, well, which is good for speed, and from all we know, at least it's secure as AES, called SALSA20, it's a stream cipher. So we use this key that we got from the Diffie-Hellman key exchange as a key for the stream cipher. And that's now dealing with your message. So the message comes in only in the stream cipher encryption. And we also add authentication. So if you have a message which is several packets long, you don't want to do a Diffie-Hellman key exchange all the time. You do the Diffie-Hellman key exchange once. Now you both have a shared secret, and you use this for authentication. Now, authentication is something where you and the other partner are convinced that you're communicating with each other. It does not convince anybody else of this communication, because an authenticator is something that both sides can compute. So Poly 1305 is a message authentication algorithm which uses the shared secret. That is enough if you're communicating with somebody, but it's not enough if you need to sign, say, legal contracts. If you want to have signatures, so you don't care about encryption, but you do care about having everybody be able to verify the authenticity of a message, then you need signatures rather than authenticated encryption. And so that is our second primitive. So for signatures, we use something which is fairly close to ECDSA, just more efficient and better. We use it on an Edwards curve. So we take the same curve that we have over here and translate it over to Edwards curve. So there's one curve, there's one security assumption that, namely, well, you can break the security of this one, then you break both of them. But our assumption is, and our tests are, that this curve is good, and then we look at two different ways of writing it. For the authenticated encryption, we use Montgomery representation because of the nice side channel resistance. For the signature scheme, we need to be able to add points afterwards. We need to have full X and Y coordinates. So there we use Edwards curves. But in the signature step, we have a fixed base point. So we do this, basically what Rachel suggested. We have pre-computed powers of 2 times the point, and even powers of 2 times the point with some scalars. So we're doing a windowing-based fixed base point scenario. So that's how we do the scalar multiplication in the first step. Now, ECDSA went like that. You have your public key, you have your secret key, and if you want to sign something, you pick this random nonce, the K. You get it from somewhere, and then we do the K times P. That's we do the fixed base point with windowing. Now, in light of the Sony PlayStation and also in light of some patents that have expired by now, we can actually do something much better. We can make this K be deterministic, but secret. So we don't need to waste more randomness from the computer, and we make it message dependent. So we totally avoid the problem that Sony fell in. What we do is, when we generate a key, we generate one secret string. That's a secret key. And now the secret key gives us the A, which belongs to the public key, and also gives us some other string B. So there is one string B which only I know. And I use that to kind of salt the hashing of the message. So to get my randomness K, I take this B, which is secret, and M. So nobody else knows B, so nobody will be able to get the K. So the first attack I showed you, nobody will get my K because they don't know my B. So this hash computation is not visible. I don't need a random K, I just need to have a random looking K. Now the second attack was, don't ever use the same K twice. If I take a hash function and it's worth its money, then it is collision resistant. So it will not give me the same output for any two things. So if I put in two different messages here, then the Ks will differ. Then I usually get the question, but what if you put in the same message again? Okay, if I put in the same message again, then of course I get the same K. But if you remember how the Sony attack worked, it was the difference of the S's divided by the difference of the messages, basically. If the message is the same, it's no problem that the hash value is the same. So it is a per message randomness that is secret. So nobody else can compute this K as long as I don't know B. I mean, if I'm able to keep A secret, I'm also able to keep B secret. Okay, another difference to the ECDSA scenario is that when I compute the hash of the message, I'm a bit more paranoid. I want to avoid that somebody who can do collisions can break my system. So I also include something extra, not just the message, which the attacker can control, but also this arm point here in the hash value. Now R will be public, so everybody else can compute this hash. So when I sign a message, then I go to the storage, I get my secret B, I compute this K, I compute K times P with this method. Then I take this is wrong. This should be H of M. Oops, I'm sorry. Replace this by H and replace this by H. So this H here, the hash of the message, comes from the hash of the message including R and P. Okay, then another difference with the ECDSA system is in the efficiency. In the signature scheme that I showed you before, I started by computing K inverse times something. Our system does not have inversions. What I have here is K, the hash of the message with some extra stuff, and the secret key. And then the verification uses the R, which is K times the point, and this one is H times the base point. So the verification equation also looks a bit easier. All of these signature schemes are equivalent from a security point of view. Unfortunately, there was something, a patent by Schnorr, which did apply to these signatures and to this stuff, and didn't apply to the ECDSA system. So the reason why ECDSA is the way it is that people try to avoid patents. It's not because it's more secure, it's actually less secure and it's more expensive, but it avoided some problems. Now, luckily, the Schnorr patent has expired, so no more problem with this one, and we can go for a nicer, more efficient, and also more secure scheme. And it's a scheme where batch verification is easier. I'm on purpose leaving out the mod. Well, mod L comes in here, but I don't use R mod L. I'm sending R itself. So everybody gets R. And the nice feature of that is that you can batch those verifications. So if you want to compute a batch of, say, 100 signatures, what you do is you pick 100 random scalars Zi, and then you take the first part, the second part of the signature here, compute this scalar, that's just one number, so this is just one scalar multiplication. Then here, it's as many messages you have, so 100 scalar multiplications, and here the scalar is coming again, but just as one number. So if you have 100 signatures batched, it's 102 scalar multiplications. So if it's 2 more than the number of signatures you're verifying, you run the Bose-Coster and verify all of them together. So that's where the Bose-Coster came in. Now, if you don't want to do batch verification, then, well, you just compute this one using the joint doublings idea I explained before. At this point, I don't need to these are public operations. I'm working on public data, I'm verifying things. So I don't need to worry about side channel attacks. So there we just use the most efficient methods. We do worry about side channel attacks in the secret operations over here. And at this point, Dan was volunteered and hopefully is still willing to.
Right. For a moment before I show the SALT web pages, let me show the benchmarking web pages that Tanja mentioned. This is the eBats and eBax and eBask and eBash projects, which are all eCrypt benchmarking of something or other, like eBash is eCrypt benchmarking of all submitted hashes, and eBats, which she mentioned, is eCrypt benchmarking of asymmetric tools, or something like that, asymmetric systems. If you go to bench.cr.yp.to, then you find all sorts of information about, for instance, all sorts of different hash functions that we're measuring, except I don't think I'm actually online right now, but fortunately, I preloaded some web pages. You can find measurements of lots of candidates for the SHA-3. There's several finalists left, 5 finalists for SHA-3, and you can find some comparison charts of how they perform on different lengths of messages on different machines, and then on all sorts of specific machines, all sorts of data of how fast they are. Sometimes you see little red marks on this data. This is something which you don't see on most benchmark data. The red tends to indicate this is unreliable data. For some reason, this measurement, we have a median, which is quite different from the quartiles of doing several measurements. If you see red for any reason on these pages, then that's kind of scary. Something went wrong. Most benchmarks will just report the median or the average, so they won't even know that something is going wrong. And there are some machines where you'll actually see a whole lot of red, like here's a machine with all sorts of weird things happening in the data. Most benchmarks will just blithely report, yeah, there's some numbers which don't actually mean anything, but they won't realize it. Anyway, there's hash data. There is public key data, which maybe is the next page. Yeah, here we go. So on some random machine, some Westmere, so this is not the latest Intel chip, but it's one of the most common Intel chips around today. This is a Xeon E5620, which is similar to some desktop Westmeres that a lot of machines have. On this particular machine, there's a first column here, the cycles to generate a key pair for different systems. You see on the top of the list here is ED 25519. That's exactly this signature system that you just heard about using elliptic curves, using Edwards curves in this particular curve 25519. And being at the top, well, it's 93,000 cycles to generate a key pair, and then some 512-bit DSA system is taking more cycles to generate a key pair. Cycles like on a 1 gigahertz machine, there are 1 billion cycles per second on each core. And then the list keeps going through lots and lots of signature systems. Now, maybe key pair generation is not the most important operation. So how about, let's look at the signing time. And then you see there's some interesting systems at the top here. And actually, the Edwards curves are a little bit far down in the list. Where are they here?
About the first rate.
Oh, yeah. Oh, okay. So cycles to sign, 87,000. There are some faster systems. Maybe I'll peek at another column to give you an idea of why we kind of disregard. If we say elliptic curves give good performance, Edwards curves and this particular curve give good performance, hey, what about this system which is signing in 2,000 cycles instead of 87,000 cycles? Well, if I flip over to another measurement from these benchmarks is how big the keys are, and you'll see how many bytes there are in keys in different systems, like 64 bytes in the secret key, 32 bytes in the public key. That secret key was the A and B that you were just hearing about. If you go down in this list a little bit, then eventually you get, here were those MQQ SIG systems with a 400-byte secret key and a 200,000 byte public key. So we kind of ignore that system as something that could actually be used on the internet, although it's not inconceivable. I mean, you can fit a 200,000 byte key onto a hard drive, and then maybe you care more about the signature performance. Hey, it even fits in RAM, almost in well, okay, level 2 cache, almost level 1 cache on some computers. Verification speed. So this is where people say, okay, RSA, for instance, 768-bit RSA. RSA with exponent 3, very fast verification, 48,000 cycles. And that is quite a bit faster than the 270,000 cycles for the signature system that we like. If you use batching for this signature system, it gets about twice as fast, even a little better than that. Still not as fast as 48,000 cycles for 768-bit exponent 3 RSA. Of course, the only problem with 768-bit exponent 3 RSA is it's broken, completely broken, but you can scale up the security level. 1024-bit is still okay. 2048-bit, this is about the speed we get for batched elliptic curve signatures, and it's still a lower security level than batched elliptic curve signatures. If you're using 2048-bit RSA and you look at the signing time, then somewhere down in this list is here we go, 10 million cycles to sign using a 2048-bit RSA key. And that's a huge performance loss compared to the 87,000 cycles for Edwards curve signatures. So, okay, these are some of the benchmarks that are available online on bench.cr.yp.to. And let me now flip to web pages for the cryptographic library. So this is, if you go to salt, NaCl, salt.caseproject.eu or salt.cr.yp.to, then you get this introduction to the library and some information about who's contributed to it. And then there's a page with why we think you should use this instead of other libraries. Plus, as Tanja mentioned, we have a new paper which is going through lots of security benefits of this. There's still some things which have to be done in the library. So for instance, the Python here, you'll see it says support for Python is a high priority, which does not mean that it's there yet. It's going to be in the next version, but it's not in the current version that you can download. And similarly, if you look through, you'll find some things which are mentioned as, well, you can expect these to come up, but it's still to be done. Now, on the other hand, some things like having the same interface in C and C++, but also taking advantage of C++ to the extent possible, that is in there. There's lots of things which are supported by the library already, and that's why it's already being deployed in various applications like DNS crypt. Flipping forward a bit to how you actually use the library. The basic interface, if you want to make a key pair, for instance, in C++, then you call this CryptoBox key pair function, and you have as a return value the public key, and then you also have to pass a pointer to where this will put the secret key, SK. In Python, it's two separate return values, PK and SK. If you get PK and SK backwards, then nothing at all will work, so the first test you try won't work. Don't worry about things that might conceivably go wrong. You'll find them out if you try actually doing any cryptography. Once you have a key pair, then you can encrypt a message with a CryptoBox function. That's what Tanja mentioned before. That's what does, in one step, it'll do the elliptic curve Diffie-Hellman, and it'll take a nonce, and it'll take, so the Diffie-Hellman is using the public key that you're sending to the secret key of yours that you're sending from, the nonce of this message. You can count 1, 2, 3, 4 as your nonce, and then the message, and it gives you back an authenticated ciphertext. And then the receiver gives that ciphertext to CryptoBox open, flipping the keys around, and gets back the original message. And that's the basic CryptoBox interface. And then CryptoSign, is a few pages forward here, is even simpler. CryptoSign, same kind of key pair setup. CryptoSign key pair gives you a public key and a secret key. And then if you want to sign a message, then, well, you just pass the message and your secret key to CryptoSign, and you get back a signed message. And these are all just C++ strings. You can output them or put them in a file, whatever you're trying to do with your signed messages. Then when somebody receives a message and your public key, then they say CryptoSign open, which opens up the signed message using your public key and gives them back the original message. And if that fails, then this function will raise an exception. And, well, in C++, you can catch the exception and decide what to do with it. So that's the basic interface. Underneath all this, there are various other functions that you can use if you like. There's various levels, like crypto scalar mult is a lower level scalar multiplication function. But I think in all of the prototypes and deployment of cryptographic code that I've done, I haven't actually had to use this crypto scalar mult for any reason. It's just the internal structuring in the library, which is used inside CryptoBox. Similarly, there's a crypto secret box, which is after you've done the Diffie-Hellman, and there's crypto hash and crypto stream and various other things. But you don't need those. You can just use CryptoSign, and CryptoSign is going to sign a message for you. CryptoSign open is going to open up that signed message, give you back the original, and CryptoBox and CryptoBox open, along with the key pair functions. So it's a very simple interface, and already there are enough applications using this that I think we can confidently say it's a reasonable interface. It's something that actually supports cryptographic applications. If you are interested in lower level stuff, let me point out, as I'll peek at a little bit of code in just a moment. Crypto verify. This is something which libraries have been getting wrong for many, many years. And it's just one example of what you have to do right to make a cryptographic library actually secure. What crypto verify does is it verifies that one 16-byte string is the same as another 16-byte string. Now, this sounds like, okay, this is completely trivial. You just say is the first byte of one string the same as the first byte of the other, and if it's different, then you say, no, the strings are different, and then you look at the next bytes, and so on. There's a standard memcomp function that does this for you. There's lots of different standard functions which do this, except what I just said for how, of course, you can do this is breakable. When people use exactly what I just said inside IPsec, then it lets people trivially forge IPsec packets. It's something which is broken one piece of cryptographic software after another, because that comparison of the first byte to the first byte If those are different, then you stop. You're taking not very much time. And like Tanja was saying, we want to take the same amount of time for a cryptographic operation independently of what the inputs are. And this crypto verify will take the same amount of time no matter what the X and Y strings actually have. Let me peek at the code just to show you. It's easy for something like, oops, there was a question, yeah. The question was, okay, what about things like RSA, OAEP, et cetera, et cetera? Yeah, all of the padding, all of the hashing, that is all in here. Everything that's necessary is done. So this is supposed to be production quality. You're allowed to use these things in real cryptographic applications up against, say, the US government, the Iranian government, Cisco, 5,000 PhDs, whatever your attack model is supposed to be. This is serious cryptographic software. It's not just a toy interface. Yeah. The library, sorry, go ahead.
So memory attacks can be
Okay.
as it is running on user space.
Okay, so the question was, first of all, is it user space or kernel space? This is actually, so the memory usage in this code is extremely constrained, so it is suitable for putting into the kernel. Now, nobody has actually put this into any operating system kernels yet, but this would be a good thing to do for exactly the reasons you're talking about, that some kernels, I wouldn't say the Linux kernel, but some kernels are very good about keeping track of their memory and making sure that nothing bad happens with them, separating drivers from other parts of the kernel and so on. And in that case, you can get much better protection for your cryptographic data than you can if you have stuff outside the kernel. Having said that, typically you'll have reasonable security on if you just have a separate process which has your cryptographic data in that process. And there's standard operating system features to clean up the data, lock memory, if you like, clean up the data that's being used inside your cryptography. But yeah, it's definitely an issue if you have data, cryptographic data stored in RAM. Then you have to worry, okay, can somebody look at that RAM?
Like crypto API in Linux, whether this type of library is going to be implemented in Linux kernel? Is there any already who is working on it?
So the question was, is this going to go into the Linux kernel? I'm not aware of any current efforts to put this into the Linux kernel. The main application area that's motivated actually deploying this library so far has been applications where people are not using cryptography because getting high security cryptography is just too slow. It just doesn't work. And we're providing high security cryptography at good speed, and that's not something where we need to be inside the kernel to make that work. So, so far, getting something into the kernel hasn't been the highest thing on the priority list. Right now, honestly, the highest thing on the priority list is smartphones. So getting ARMs running really fast for this software, that's the top thing that we're working on. Okay, let me just peek at this crypto verify code just to give you an example of the user displaying this is called movie. Let me just do this without the D, without the L. So there are several directories inside the SALT distribution which are the different crypto functions that you might use. For instance, crypto box and crypto sign and so on. And the one that I want to look at is crypto verify. Now inside, actually let me just do one more ls. Inside each of these directories there are the different functions that implement that type of cryptographic operation. So an operation like crypto hash in the middle there. Crypto hash SHA-256 and crypto hash SHA-512, those are both doing crypto hash, but they're different cryptographic primitives, different functions. One's producing 256-bit hashes, the other one's producing 512-bit hashes. As a user of the library, if you want to select one of those, you can just say crypto hash SHA-256 or crypto hash SHA-512, or just say crypto hash and trust the people distributing the library, namely us, that we've selected a reasonable crypto hash for you. Looking inside crypto verify, let me actually show you one more level of subdirectories. Inside each of these directories, there are multiple implementations. For instance, the signature scheme that you were just hearing about has a reference implementation which is not as fast as the 64-bit optimized implementation. And in general, for each function, we'll have the optimized implementations for whichever machines. Again, smartphones, ARMs are the top priority right now. And then, actually there is some ARM support in there already. And then there will be some portable backup. And then when you compile the library, then the script that does the compilation will try each of those and take the fastest working implementation of each function. And finally, looking inside, say, crypto verify, what the code looks like. This is code which is doing just some logical operations with no branches, no ifs. It's just going through byte 0 of x and byte 0 of y and byte 1 of x and byte 1 of y. And at the end of the day, computing something which is, if you look at this for a moment, going to tell you whether x and y are the same string or different strings with no branches. There's no ifs. There's no things which are actually implemented as ifs like equals equals depending on any secret data. So everything here is public computations in terms of which instruction is going to be executed. All of the loops, it's totally public. Everybody knows how long the loop is going to go, what's going to happen next. Move the window. Oh, it's looking, I'm sorry, a little bit different on my screen from the projector screen. I'm sorry about that. There we go. Okay. Yeah, I guess I got the font size big enough, but didn't get the alignment. Yeah, so this is the crypto verify function. And it's just a small example of how at every level of the implementation, we're extremely careful with any software side channels. So there's no leakage of any, there's no exposure of any secret data to the branch unit, and there's no exposure of any secret data to the address bus, the cache addresses, for example. So we don't have any possible cache timing attacks. Let me show you one more code example, and then I think it's about time to stop. Oops, which directory am I in? Crypto sign. And now ed25519. Let's look at the reference code, because I don't think you want to look at the optimized code right now. Inside here, there's various .c files, and let's look at, in particular, the cmove function. Equals an even better example just for very simple little computation. This is just taking two 32-bit unsigned integers and asking, are they equal? And you would just think, say, if A equals B, or, well, return A equals B, except, well, that would be an if, and we don't allow that in this library. So we say take A XOR B and then do something with it, some subtractions and shifts and things that take constant time, things where we don't have to worry that the CPU designer being careless about the branch unit and the cache and so on. We don't have to worry about that exposing any of this data because we're not doing any of those operations. And then if I, somewhere in, I think it was here, yeah, here we go, cmove. This is a conditional move operation, which maybe the CPU has as an instruction, but portably you can do some logical operations, some ands and some XORs, which will take one input and conditionally move it onto another input depending on whether some condition is true or false. And that condition is this mask, and if you look at what these ands and XORs are doing, then you see it's putting onto the result either one input or the other input, depending on this bit, in a way that does not have any secret ifs. There's this for loop which is going 32 times, but that's public information. And similarly, at every level of the code, we're making sure that we don't have any secrets inside brackets, any secrets inside ifs. The highest level version of this I'd like to show you is the usage of cmove inside. Let's just grep for it. This particular code was from Peter Schwabe. So cmove, here we go. This is taking a table of pre-computed multiples of some p. Before you were hearing about some p, maybe 0p, 1p, 2p, 3p, and the 0p maybe doesn't have to be stored, and then 4 times those and 16 times those and so on. That's what's stored inside this table, G25519 base multiples affine. And then the cmove is conditionally picking up one of those using this equal operation that I showed you, depending on some bits extracted from an exponent. And nowhere here are there any ifs. We're looking at every single element of the array and picking them up and doing arithmetic on those elements instead of doing a variable array index, which is something that can allow attacks and has allowed attacks. These kinds of attacks are why AES keys were extracted from the Linux kernel in 65 milliseconds. This is why OpenSSL has been repeatedly broken. This is why DTLS was just recently announced to have been broken. And we avoid all of those dangerous operations in this library, while at the same time providing very, very good speeds and very high security. Okay, so I think that's all I wanted to do for the show and tell, and I should give things back to Tanja. You didn't have anything else to say? Well. Broken, like DTLS, well, the report is that both the OpenSSL and GNU TLS implementations of DTLS expose plain text. In the case of GNU TLS, it's partial exposure of plain text, and for OpenSSL, the announcement was complete exposure of plain text. Now, I assume that this exposure means something which takes some amount of interaction with the server, and I don't think the paper is online yet.
I have nothing else to say. I'm just here for questions. So.
All right, well, in that case, thanks for your attention.
So something that we dealt with Tor, we were trying to produce a time-independent string compare function, and we found a Microsoft compiler that looked very thoroughly at everything to try to figure out if what we were doing was like a string compare, and then they would replace our code with a call to the Microsoft string compare function. So we found that Microsoft broke our time-independent comparisons because we looked too close to what they knew we were trying to do.
Yeah, ultimately we want everything done in assembly language. Actually, there are some assemblers which try to screw things up as well. So the right thing to do is actually generate binaries. We're not all the way there yet, but that's the ultimate goal. There's no reason to rely on some compilers which were written by people who don't care about security. I don't mean to say that Microsoft particularly doesn't care about security.
This question about NAF. Just now you wrote about that NAF. If we represent the number in binary, or you can represent in NAF. So NAF will always may not always be better than binary if we are using the sliding window. So what is the probability that it would be as good as like if you represent a number in NAF? What is the probability that you select a random number and you represent in NAF as well as binary? What is the probability that NAF will be as good as binary?
You mean as good as in the sense of has the same number of additions and doublings?
Yeah, same number of doublings and additions, yeah.
Well, on average, the number of additions in the non-NAF, in the binary representation, is 1/2, and on average, the NAF is 1/3. Now, for NAF, you know that there is always a 0 after each one. So the number of additions in the NAF is at most 1/2. Because after each addition, you have a non-addition. So at most 1/2. So in almost all cases, the NAF is better. I can't give you the percentage, but just knowing that the binary is between 0 and 1 with an average of 1/2, and the NAF is between 0 and 1/2 with an average of 1/3. It's never worse, it's almost always better.
So like cases like 35, these are all outliers.
So the 35 case is where it doesn't help you.
Yeah.
But usually it does help you. I mean, if you start with something which has no adjacent coefficients, then it doesn't change it at all. So it doesn't always get better, because sometimes you start with an integer which already has the property that there's no adjacent ones, and then it doesn't change it.
Yeah, one question is related to the authenticated encryption actually. You told that you use poly 1305 for authentication and salsa 20 for encryption. Any specific reason is there, or?
Well, the main reason is speed, and then, well, Dan will say that he trusts his functions more than other functions.
No,
I trust his function at least as much as other functions.
No, that
But-
is that
so-
is correct. But you are going to 2 pass in that actually. That will take more time. Is there any primitive which will do these 2 things together actually?
That is a very interesting question. So let me do some product placement here, some advertisement. So right now everybody is still busy with the SHA-3 competition. What we're trying to organize starting next summer with the pre-round is a competition on authenticated encryption. So we are asking ourselves, what is the best way of doing this operation? Is it the best to do an encryption and a MAC?
Yeah.
Or is it better to do one
MAC
combined thing?
Yeah.
I hope I can give you the answer in 3 years. And if you have a good candidate, then if you're not totally busy with the SHA-3 competition, it might be a good time to start polishing that. Any more justifications of poly or salsa? Implementation ones? Easy to implement.
Well, yeah, I think for me, main motivation for being very careful with AES is that it's very difficult to implement AES in a secure way. There have been so many cases of people implementing AES and getting into trouble with side channel attacks. Even for software side channel attacks where we know exactly what causes those attacks and in principle we know how to avoid them, people still get in trouble again and again and again. If you try to implement AES in a way that works around those, then you can do it. It has been done. We actually ship in this library a secure implementation of AES, but it's pretty damn slow. We've done everything we can to take the best stuff out there, but it's not going to give you reasonable speeds for typical applications. If you're, yeah, since Shai Garan is in the audience, I suppose it's a good moment to mention that yes, the new Westmere and Sandy Bridge and forthcoming Ivy Bridge Intel processors and the Bulldozer AMD processors and some other processors like the VIA, Eden, and Nano processors, and actually the UltraSpark, the ROC processor, although that one's been canceled. Anyway, there are a lot of processors out there that include AES instructions. So if you have one of those processors, then you can run AES very, very quickly. And those implementations are certainly not going to have any side channel problems at the software level.
I heard some Intel came with the implementation in single clock AES actually. I don't know if it is true or false.
From performance measurements, well, we have, so sitting 1, 2, 3, 4, 5 rows behind you is the person who got AES actually into the Intel chips. And he can tell you all about the performance of it. But having said that, it's reasonably clear that from performance details that the current implementation has 4 S boxes in parallel. So if you want to do one AES round, then you have to run through that 4 times. So there's a latency of at least.
He says no.
You have 16 in parallel. Then what's accounting for the latency? Okay. Something is making an interesting latency slowdown in the AES instructions. Realistically, you will get performance better than 2 cycles per byte for AES in a reasonable mode, say counter mode, on these Intel chips. And then, I don't know, maybe, so Shai is giving a tutorial on Wednesday afternoon in which he'll say how fast various things are on the latest Intel processors. And perhaps he'll mention, not that I have any inside information, but perhaps he'll mention something about how fast AES is on the current and future Intel processors. And so I guess you'll hear much more about that. But it's certainly excellent performance. On the other hand, if you have an ARM Cortex-A8 smartphone, then it's a quite different performance picture for AES. You want something that does well on a big Intel processor and a big AMD processor and a smartphone and smaller devices, then you end up choosing functions which might not be the best performance for a particular one of those. And certainly the carryless multiplication, PCL-MulQDQ in the current Intel chips, wonderful instruction, and I don't know, maybe we'll hear something about that on Wednesday afternoon as well. Some forward references to the Wednesday tutorial. Yeah, there's certainly all sorts of interesting things you can do speed-wise with that. Poly 1305 is not quite as fast as what you can do with binary functions using PCL-MulQDQ, but on the other hand, it's much faster on a smartphone or even slightly older Intel processors.